All right, so enough with the history lesson and the old periodic table. Let's look at the modern periodic table. So we look at our elements today and organize them by atomic number, and we focus on identifying an element by its atomic number. Back in the day, Mendeleev was focused more on mass, which for the most part is fine, that the elements do increase by mass, but focusing on atomic number made it a lot easier to identify new elements, and that was kind of the work of another chemist called Henry Moseley. Moseley said, let's instead focus more on atomic number, because the atomic number increases by the same increment from one element to the next. It always increases by 1. So now if I've got a gap in atomic numbers, I know exactly what elements are missing, and I know what those atomic numbers are. Whereas when you focus on atomic masses, they do increase, but they don't always increase by the same increment. And in fact, there are a few times when they don't increase. For example, from tellurium to iodine, number 52 to 53, the mass actually goes down just a tiny bit. And it's because of neutrons. The atomic number goes up by 1. Tellurium is element 52, and iodine is element 53. It's just that there's a little bit less neutrons in most atoms of iodine. So the mass drops just a little bit. But when we organize the elements by atomic number, we see patterns in the properties of the elements, and we form these groups of elements with similar properties, and that's basically called the periodic law. We're going to look at groups going up and down. Say normal periodic tables will have 18 groups going up and down the periodic table, because normally the F block is pulled out and kind of just put on the bottom of periodic tables, and for real, just so that it fits better on a standard sheet of paper. It's just a little easier to manage. And those elements in the F block, eventually we're going to call rare earth metals, and they are very rare, unstable, radioactive, often synthetic, that they don't really occur in nature. They're formed in a lab, and so often we pull that out. But this is what the periodic table would look like if we had that F block in there, and the atomic numbers increase steadily going across, and we form these groups going up and down, and the groups have elements with similar properties. And then we also look at the horizontal rows. Those are called periods. And so if I say I have an element in period 2, it means it's in the second row of the periodic table. So we'll be referring to elements by their groups and by their periods. Now, one other thing that we kind of know about the periods, the rows going across, that is directly related to the energy levels. So if I say that I have an element that's in the second period, then I know that it's got electrons distributed amongst 2 energy levels. And eventually we're going to find that there are similarities in the atomic structure of elements in a group going up and down together. Now, we already looked at the trend a little bit in valence electrons, and that they're all going to have the same outer electron configuration. If I look at atoms from one particular group going up and down. I like question 4 a lot. So recently, within the last few years, the 7th row of the periodic table has been completed. And we know of elements up through 118. They all have names and they're official. They're on the periodic table. Sometime in your life, I'm sure there will be 119. Predict where it would be placed on the periodic table. Explain your reasoning. Well, a couple things. If the atomic numbers just increase going across, if I ended the 7th row or the 7th period with element 118, then I would certainly expect 119 to maybe be like right here. It would probably start the next row of the periodic table. Oh my gosh, how cool would that be? Its outer electron configuration would be like 8s1, right? Whoa, cool. Someday, I bet you'll see it. Explain my reasoning. And so, yeah, that might be it. That maybe I explain that atomic numbers increase by 1. And so if I ended the 7th period at element 118, then 119 should start the next row, the next period. Maybe it would be based on properties, that if I could study the properties of element 119, if they're similar to number 87, francium, then that might give me more support for putting it as the next element in that first group going up and down. Other general properties that we can note of the arrangement on the periodic table, we should be somewhat familiar with metals, nonmetals, and metalloids. So most elements on the periodic table are metallic. So they're showing kind of these yellow ones as being metals. Even down in the bottom, often we call the F block the rare earth metals. Most elements are metallic. The nonmetals are kind of shown with this, I don't know, light green color. So these are my nonmetals. Just a pretty small section of elements in the upper right-hand corner. A lot of them are gases. And then most periodic tables will have this staircase that kind of goes zigzag through the P block. And the elements along that staircase are often referred to as metalloids. Metalloids. Okay, so metals. We are familiar with metals. Typical properties of metals. I mean, it says that most of them are solids except for mercury. I would maybe know that metals are shiny. We call that luster. They're ductile and malleable. Ductile means that you can draw metals into a wire, like a thin wire. Malleable, you can pound it into a thin sheet. Metals often have high melting and boiling points. Keep these out of the way. Melting and boiling points. Metals are great conductors. They conduct heat and electricity. And eventually we'll learn why. We'll look at the structure of metals, like the atoms that make up a metal. And there's kind of a reason why they end up being ductile and malleable. Like you can move them and shape them. And there's a reason why they can conduct heat and electricity, and they have high melting and boiling points. The nonmetals, on the other hand, are often solids, but they could be gases. There's one liquid. Bromine is naturally a liquid. You've got like your nitrogen, oxygen, fluorine, chlorine. Obviously your last group, helium, neon, argon, a lot of gases. Some of them are solids though, like your carbon, phosphorus, sulfur, selenium, iodine. Those are solids. In general, nonmetals are not shiny. They're pretty dull. They're not ductile, malleable. We often say they're brittle. You can kind of scratch them with your fingernail. Like, think about a piece of charcoal. Charcoal is carbon. You can scratch it, but if you like pound it with a hammer, it's just going to crumble. They do not have high melting and boiling points. Low. What if I just say MP and a BP for melting and boiling points? And they are poor conductors. I mean, we don't make wire out of carbon. It doesn't conduct heat and electricity, and it would just crack on you. Well, then there's this goofy group of elements that are right along that staircase. These ones that are kind of in the dark green. The metalloids seem to have properties right in between metals and nonmetals. So they're shiny, they look like metals, but they're often kind of lightweight. Normally you have a butcher play with them. And so they on the surface seem like a metal, but then you put it in your hand and you're like, whoa, it's like really lightweight. Or like that gallium. We looked at gallium earlier. Gallium looks like a metal, but it's got a pretty moderate melting point. Like I have to warm it up in my hands, but it'll go from a solid to a liquid with just our body heat. That's kind of unusual. Some of them are conductors, but they're kind of moderate conductors, which is sometimes a good thing. Like question 5 says, from which area of the periodic table are you likely to find semiconductors? That's these metalloids. The metalloids. And sometimes you may want something that only conducts a small amount of heat or electricity, and that would be your metalloids. Often you can mix elements, and like you can mix metals and metalloids to make a final product that has the exact properties you're looking for. Pretty cool, huh? So we can group elements very generally by whether they're metals, nonmetals, or metalloids, and we kind of could predict some of their general properties then. Maybe a little bit more specifically, we can look at some groups of the periodic table that have kind of unique properties. So the first group going up and down, we call these the alkali metals. So they're in red, the alkali metals. Now this does not include hydrogen. Hydrogen has a little bit of an identity crisis, kind of like helium. But for electron purposes, we put helium kind of next to hydrogen because it fills the 1s orbital with 2 electrons. But on the periodic table, helium is left in this last group. It is a noble gas. It's a non-reactive gas. It has all the properties that are similar of neon, argon, krypton, xenon. It's not at all like beryllium, magnesium, calcium. So helium gets to go with his buddies that have the same properties. Hydrogen is kind of in the same boat, but we put hydrogen in group 1 based on his electron structure. He's got 1 electron in the outer s orbital, similar to lithium, sodium, potassium, beryllium, but it's not a metal. So technically the first alkali metal is lithium. And these are those elements that are really unique in that they're metallic, but they're soft. Like that's not normal for a metal. You could cut a metal with a pretty dull knife. And they're crazy reactive. They are the most reactive metals on the periodic table. Weird. They'll react with air, they'll react with water, not normal of a metal. The second group, these are my alkaline earth metals. Here's how I remember the two. Alkali, group 1, it's one word. Alkaline earth, it's group 2 because it's 2 words. Brilliant, right? The alkaline earth metals are still pretty reactive. Like we put calcium in water and it fizzed and bubbled and gave off a flammable gas. That's not normal of a metal. They still react with air, so often they don't look real shiny on the surface because they'll react with oxygen and get this little oxide coating. They're just maybe not quite as reactive as group 1. In the middle, these elements that are kind of in the tan color, I don't know if it officially says it here. Well, kind of, I guess, at the bottom. These guys are called transition metals. I'm going to write that in here. Transition metals. Now, technically, these guys on the bottom, like the F fillers, those are often called rare earth. I might put that in here, too. Rare earth metals. And these are all technically transition metals, but sometimes we call the bottom groups rare earth because they are really rare. But often this is where you'll find your typical metals. This is your chromium, iron, cobalt, nickel, copper, zinc, silver, gold, mercury, which is kind of a goofy metal in that it's liquid, But the transition metals are where you find metals with pretty typical metallic properties. Then we get over into the P block, and there's really no fancy name for the boron family, carbon family, nitrogen family, or oxygen family. Just kind of is what it is. But then the halogens and noble gases will finish her off. The halogens are in pink, the noble gases, the non-reactive gases, are in purple. I kind of like the halogens. They're really reactive nonmetals. They're the most reactive nonmetals. And some of them are kind of interesting. It's cool that like fluorine and chlorine are gases, bromine is a liquid, and then iodine, astatine, and tennessine, which is the newest of the halogens, number 117, they're all solids at the bottom. So they start with gases and then move to a liquid in the middle, and then they're solid at the bottom. But none of them, even the solids, none of them are metallic. So here might be a little more specifics that we could get by knowing where an element falls. Not only is it a metal or a non-metal, but in what group is it? Which then I guess brings us to number 6. Choose an element from the periodic table and describe everything you might know about it at this point in time. That could be any group. And so maybe you pick an element and you describe whether it's a metal, non-metal, or metalloid. And then if you picked one of these special groups, the alkali metals, alkaline earth, halogens, or noble gases, maybe that gives you a little more to go on for number 6. Eventually we'll look at some elements and look at some of their more unique properties. And then finally, that brings us to nearly the end of this section. Number 7, lots about patterns. What patterns did you observe in the development of the periodic table? How were the patterns related to the timeline? And so I think obviously we could say that there are patterns in mass, there are patterns in atomic number, there are patterns in properties. The periodic table is obsessed with patterns. How are the patterns related to the timeline? I think they just get more and more sophisticated as time goes by, and we've got better lab equipment. We can run more sophisticated experiments, and we can study the properties of these elements more closely. That just helps us to gain better data on each of the elements, and then we can make better observations with their patterns and predict new elements and new patterns better.